Beginning in the 1960s, the concept of digital computers being introduced in aircraft was becoming a reality within the USSR, especially considering that towards the end of the decade, analog civilian and military computers alike were being phased out in favor of more advanced transistorized models. It only made sense that this renaissance in versatility and processing power would extend to aircraft, which in many regards would benefit the most from these improvements. As a result, the ODCM, or Onboard Digital Computing Machine, entered the minds of many engineers across the Union, as it was the ODCM that held the key to the incorporation of more advanced control laws for the aircraft and its subsystems. Previously, information could not be directly exchanged between individual subsystems, but with the digitalization of existing technology, what was described as a unified equipment complex could be introduced, which would yield considerable benefits in safety and efficiency in which missions could be executed. The unification of subsystems would also reduce the cost of future modernizations. While the ODCM was exceedingly promising, there was a lot standing in the way of this new technology. First, a computer would need to be developed, after which an information exchange system to ensure that everything aboard the aircraft could interface without complication. And lastly, software would have to be developed. While the first two steps are obvious, software development was initially out of sight, and therefore out of mind. In many regards, software development actually represented a far greater challenge than the creation of new domestic computers, and was significantly more expensive. This was due to the fact that beginning in the mid-1950s, a wealth of experience was accumulated in the creation of prospective digital computers for use on aircraft and missile systems alike. Many of these remained little more than prototypes, due to a lack of demand, with the exception of one, Plamya VT, created by NE-17 of the Ministry of Radio Industry. This was especially interesting, as historically the Ministry of Radio Industry did not handle the production of computers. They worked with computers in that they were often tasked with integrating them into existing avionics packages that they had assisted in creating, but digital computers were never their specialty. This was handled by Elektro-Avtomatika in Leningrad and NICEVT in Moscow, who designed and produced computers for the Ministry of Aviation Industry, who needed them for navigation and targeting systems that they had been tasked with creating. As a result, the experiences gained from Plamya VT were primarily employed by Elektro-Avtomatika and NICEVT, not NE-17. As we just discussed, there was indeed interest in digital computers aboard aircraft, but there was little incentive at that time to adopt them. And then,
This is Ed Murrow, and this is the nuclear submarine George Washington. Beneath each of these hatches will be a 28-foot Polaris missile designed to fly 1,500 miles, eventually 2,500 miles. These hatches normally open at launch depth, the natural habitat of submarines. Since 1945, when man first unleashed the force of the atom and fashioned it into a bomb, he has been faced with the problem of getting it on enemy targets. Now, the year of the Polaris, a three-stage missile, whose first stage is really a 380-foot submarine that can go around the world on a core of uranium only slightly larger than a golf ball, and which can fire 16 hydrogen warheads without ever surfacing.
Admiral Rayburn, they do look like the doors of doom, don't they?
This monumental shift in the nuclear strike capabilities of the U.S. forced an immediate investment in advanced anti-submarine defenses. to significantly extend the ranges in which these threats could be detected and destroyed. Analog computers of yesteryear just wouldn't do. With a considerable sense of urgency, a digital computer and integrated unified equipment complex had to be developed from scratch, and introduced in short order on IL-38 and Tu-142. OKB 857 was chosen to design the computer due to its experience in the development of analog fire control computers for similar aircraft. Plamia VT, being one of the most complete proposals within the USSR at that time, was chosen for further development as a prototype for these new prospective submarine hunters. Ni-17 was tasked with refining it under the leadership of chief designer Karamanov. Meanwhile, by 1960, a crack team had been formed at OKB 857, which managed to not only produce a small number of experimental computers, but conduct flight tests with these systems within just 4 years. Viktor Lonardin would be crowned the chief designer of the Soviet Union's first digital airborne computer. The most difficult aspect of this endeavor was ensuring that this computer's software was modular, easily understandable so that it could be iterated upon, and universally compatible with future models. The emphasis placed on modularity was especially interesting, as it was in many regards a totally new concept within the Soviet computing industry, and the advantages that this would provide were not yet fully understood. These early computers were to employ double-sided text-to-light PCBs, which were relatively expensive to manufacture. Within the USSR and across the world, throughout much of the 20th century, PCBs were some of the most expensive elements within consumer and military technology alike. There were some problems at this time with the impregnation of these boards with TBDP fire retardant, which was apparently only synthesized in quantities of 15 tons per year, leading to shortages. Generally speaking, the military and space industry consumed much of the TBDP and left little for civilian goods, but this practice started in the 70s, and so it is not entirely relevant to the system in question. OKB 857 would succeed in putting 2 digital computers into service for use within new radio-acoustic ranging systems, designated TSVM-263 and TSVM-264. They differed from program requirements only in the application of simplistic single-sided PCBs. The technology was so experimental that, in many cases, individual computers within the same series could differ from one another in capability, as improvements were constantly being made with each complex produced. As these efforts transpired, lower-level command systems, such as CRAB, were entering service, which should have seen integration of their own first-generation digital computers. CRAB was designed to provide automated fire control and target prioritization for a regiment equipped with S-60 anti-aircraft guns, supported by S-75, but in reality it ended up doing the same for Krug brigades. CRAB allowed for 12 targets to be processed simultaneously, 2 of which were received from higher-level command facilities, like Vozdukh-1 or ASURK-1. It had a myriad of shortcomings, which will be discussed in a video dedicated to lower-level command systems, but it was an important stepping stone nonetheless, primarily due to the fact that the computers used by these early automated command and control systems were the first to be created under the emerging standards for digital computer development. Despite this, these early command systems were simplified and made largely semi-automatic, resulting in a regression to analog computing, which would be rectified a few years later, when it became clear that automation was the way forward. These standards outlined a research and development cycle that would be observed for decades to come. First, the computer was conceptualized, after which it was created alongside a comprehensive set of diagnostics and testing equipment. Once this stage was complete, software was developed, and then documentation outlining its functions. Despite this being formalized by GOST, many teams skipped the preliminary design stage, as they believed pre-project research and proposals to be sufficient. With the monumental success of TSVM-263 and TSVM-264, 500 of which would be produced, demand for digital computers aboard aircraft grew exponentially. This resulted in the construction of the Cheboksary instrument making plant between 1965 to 1970, with its express purpose being the expansion of production capacity within this emerging sector. Very quickly, the application of these systems outgrew anti-submarine aircraft, and expanded to MiG-25RB, MiG-27, and SU-24. However, TSVM-263 and TSVM-264 were simply too large to see integration on systems operated by the VVS. Despite this, an attempt was made to install an unacceptably large computer within MiG-25. This was primarily done to test compatibility with the rest of the aircraft, and was not intended to see service. After which an urgent weight reduction program began, alongside efforts to create smaller, less power-hungry computers that also featured greater reliability. At this time, the technology did not exist to pursue these requirements. B.E. Frodkin at Electro-Automatica would spearhead exploratory investments in miniaturization that would become a defining characteristic of what were described as second-generation digital computers. This terminology was first used in reference to a brand new series of airborne computers, the influence of which is impossible to overstate. Second-generation digital computers were characterized by the application of discrete modules. Orbita 1, being a second-generation digital computer, employed modules, designated PI-64 and PI-65. The later Orbita 10 would be distinguished by the application of Trapezia 3 hybrid modules, developed by OKB 857 and NIITT. PI-64 and PI-65 were manufactured through a highly manual process. Various components were welded onto conductive bases, which were then connected to one another via a polyvinyl chloride film strip, serving as a frame. They were then secured to an insulating base with leads for mounting the modules onto their respective boards, after which they were treated with moisture-resistant varnish. The compound used at this stage varied depending on a myriad of factors. As a result of delays, and a need to integrate these computers as quickly as possible, a set of proprietary components were introduced to streamline the production process and reduce the likelihood of errors, as these computers were already highly experimental. While this did ablate the initial investments in modularity, it was not terribly problematic. At that time especially, due to the fact that no other organization within the USSR was planning to develop software or hardware for the Orbita series. Orbita 1 was considered a replacement for TSVM-263 and TSVM-264, but was still far too cumbersome for the aircraft employed by the VVS. In 1966, engineers at Electro-Automatica began work on further miniaturization, with the intention of resolving this issue once and for all. But they were not alone. In Zelonograd, research institutes and production facilities dedicated to microelectronics were under construction, to support the Research Institute of Precision Technology, which was finally operational. These investments allowed Trapezia 3 to be finalized and ready for production as early as 1967. Trapezia 3 served as a quantum leap as far as size and weight reduction was concerned. So much so that it allowed for a wide variety of additional components to be introduced that were previously impossible to integrate, such as highly specialized multiplication and division units, which effectively doubled compute power. These modules would be employed by Orbita 10, an unreasonably successful design as far as production volume was concerned. Across 10 unique variants, 4,000 would be manufactured, differing only in the composition of their I/O devices and memory capacity. Orbita 10 was first produced in 1970 and accepted into service in 1971. Regardless of the modification, all Orbita 10 series computers are 16-bit machines, which means they can run Doom. They were produced in both register-to-storage and register-to-register formats, and were capable of 62,500 and 125,000 operations per second, respectively. The basic model used RAM with a capacity of 1,024 words, ROM with a capacity of 16K words, and non-volatile memory with a capacity of 256 words. Depending on the configuration, mean time before failure was generally within the range of 250 to 500 hours. There were considerations later down the line at Gosnias to introduce assembly to Orbita 10, but this never materialized. In January of 1970, a decision was made to modernize the MiG-25R into what would become the MiG-25RB, A prototype based on MiG-25R-4 was fitted with 2 multiple ejector racks under the wings and fuselage, which had to undergo rigorous testing against extreme aerodynamic heating. Earlier trials revealed that the standard tin-based solder would melt, resulting in premature bomb release when a certain speed threshold was exceeded. Logically, this had to be resolved. The existing Pelling D navigation system, revolutionary in its own right, required a myriad of adjustments to suit the new flight profile of this prototype, primarily the introduction of radio beacons to correct range and azimuth. This would allow for bombs to be automatically released at a set of predetermined coordinates. 2 more aircraft, number 020403 and 020601, would be converted to expand testing efforts. They would be used to trial a variety of payload configurations, which allowed for the maximum bomb load to be increased to 5 tons of ordnance, made up of 10 Fab 500M-62Ts. These munitions featured greater heat resistance when compared to traditional Fab 500s, allowing for bombs to be lofted at supersonic speeds from the stratosphere, making the aircraft effectively impossible to intercept kinematically. Polish MiG-23 MFs during joint exercises struggled to so much as observe Soviet MiG-25s when tasked with intercepting them. In one case, in 1985, visual contact was established with a MiG-25 during a simulated air attack, but it quickly disappeared into the clouds and was never seen again. MiG-25RV would pass state trials in December of 1970, and was accepted into service in 1972. Production MiG-25RBs would use the significantly improved Pelling DM navigation attack system, which introduced Orbita 10-155 and the DIS-7 Doppler system. Using this computer, MiG-25RB automatically followed a predetermined course after takeoff. When the aircraft reached the optimal position for bomb release, the pilot was instructed to pull the trigger, after which the return flight would begin to one of 3 pre-programmed airfields. At an altitude of 20 kilometers, a bomb drop from a MiG-25RB at a speed of Mach 2.35 would reach a target nearly 39 kilometers away in just 76 seconds. A bomb load of 10 Fab 500s per aircraft would be especially devastating to any infrastructure unlucky enough to be targeted, especially airfields, oil refineries, and fuel depots, as a single bomb could throw shrapnel up to 870 meters from the impact point. Additionally, a delayed explosion could create craters as wide as 12.5 meters. However, this cut the fragmentation radius in half. Orbita 10-155 initially suffered from problems related to reliability. However, the computer and Pelling as a complete system were slowly refined over time. These issues were entirely eliminated with Pelling 2, the most advanced of the series. Pelling DM had a CEP of roughly 800 meters, while Pelling 2 around 400. The MiG-25 pilots of the 16th Air Army practice high-altitude bombing assisted by Orbita day and night on Tuesdays, Thursdays, and Saturdays. Alongside Orbita 10-155, Orbita 10-15 would be developed, which served as a significantly smaller model for use on lighter aircraft, with an envisioned secondary application of increasing compute power on larger aircraft, when paired with 10-155. With the success of Pelling DM, it was only reasonable that the Orbita series see continued application. Mikoyan, having already worked with the system, jumped to integrate the far lighter variant in the improved MiG-23B that they had been tasked with creating, designated MiG-23BM. Previously, the Sokol 23S navigation attack system had been used, which was aided by an analog computer. While this system was received enthusiastically by pilots, who converted from entirely manual platforms like Su-7, it still monopolized a great deal of attention and failed to keep up with emerging accuracy requirements. The concept of integrating what was described as an electronic brain to manage the aircraft's weapon systems automatically so that the pilot could focus on the mission was exceedingly appealing. At that time, Sukhoi was also hard at work introducing their own digital navigation attack system, designated Puma-A, built around Orbita 10-058. This effort had been underway since the mid-1960s, and they had actually beaten Mikoyan to the prospective introduction of an Orbita 10 series computer, but had faced considerable difficulties in realizing the system, allowing Mikoyan to take the lead in this area, and claim considerable advantages over the emerging Su-17M2. Incorporating digital computers at Sukhoi was always a difficult task, not due to a lack of incentive or desire, but the fact that Orbita 10 series machines were not produced in large enough numbers to be introduced into existing systems like Su-17. Orbita 10-15-23 would first be integrated into the new PRNK-23 navigation attack system through 2 aircraft assigned to be produced by MMZ Zenit in December of 1971. This provided an improvement in accuracy of 20 to 30%. Orbita allowed for the capabilities of PRNK-23 to exceed the analog predecessor by a factor of 3. Alongside its improvements to the lethality of the aircraft, PRNK-23 also allowed for automatic flight along a predetermined route via 6 points, which could also serve as targets, and automatic landing at 5 pre-programmed airfields. Before the aircraft took off, 43 parameters were entered into the computer, such as present meteorological conditions and the ballistic characteristics of the munitions carried. This ensured that they could be employed with greater precision. The application of Orbita also allowed for the simplification of sighting equipment within the aircraft. It is for this reason that MiG-23BM was equipped with little more than S-17VG, which had its reticle deflection, like everything else in the aircraft, automatically adjusted by Orbita. Meanwhile, at Sukhoi, work on Puma was still underway. Jumping back to 1966, a contract was signed with Ni-131 to authorize the modification of an IL-14 to test the complex. In April of the following year, proposals were submitted, which sought to equip the experimental T-58M interceptor with Smerch 100M, in favor of Puma. This did not slow down development on the system as T-6-3 was still slated to operate it, at least as far as the July 28th proposal was concerned. Without going into too much detail on the development of Su-24, as it deserves its own video, this period was especially interesting, as Sukhoi had not yet committed to variable geometry, and was still under the impression that this would be present on a single prototype. Only in October was work suspended on T-6-3, and commitment to T-6-2I realized. Deadlines remained tight despite this massive shift, and in May of 1968, Sukhoi approved weight limits for the new design. A conclusion was reached on June 3rd, where it was decided that moving forward, the OKB's efforts would be directed towards the creation of a ground attack aircraft with a variable geometry wing. This was officially approved on August 7th, when Decree No. 600-212 was issued. 2 prototypes were to be constructed before Q4 of 1969. Further testing of Puma through an IL-18 testbed would also transpire around this time, beginning in 1968. Generally speaking, the Su-24 program was a mess throughout the latter half of the 1960s, and a coherent direction as to where it was headed was finally materializing. From this point forward, the team worked with exceptional haste. In December of 1969, the first functional Puma A prototype was installed on T-6-1, concluding a modification cycle starting in September, after it had completed 21 flights with the equally experimental AL-21F No. 85-11 and 85-12 engines, beginning in January and continuing into May of that year. Throughout much of 1970, T-6-1 would carry out 74 tests, 50 of which were centered around confirming the functionality of Puma A. In February of 1971, the recently constructed T-6-3I was transferred to Aktubinsk, where it would carry out tests to determine if Puma could effectively integrate with Kh-28. In March, the first missile was launched, followed by dumb bomb releases and Kh-23 launches towards the end of the year. It appeared that all was going according to plan, and that deadlines set for the third quarter of 1971, where a preliminary conclusion on the system would be reached, were on schedule. However, this was somewhat optimistic. Alongside a myriad of issues related to flight performance, which will be covered in a separate video, Puma A was exceedingly unreliable. It was decided that getting rid of the prototype sets and employing the serial Puma A's already being produced to greater standards at plant number 483 in Kiev for further use was a sound decision. 1971 to 1972 was unbelievably productive, all things considered. Another IL-18 flying testbed was commissioned to test the serial Puma A, while 4 T-6 prototypes flew a combined total of 254 sorties. By the end of 1972, 8 prototypes had conducted 469 flights. Notable happenings included Puma integration on T-6-1 being refined, which allowed Orbita to more effectively solve navigation and combat tasks, T-6-3I and T-6-9 successfully employing Kh-28, alongside verifying the safety of firing S-8, S-24, and S-25. T-6-4I, testing solutions for accurately firing unguided munitions, such as the aircraft's cannon and rockets while aided by Puma, and T-6-7 doing the same with dumb bombs. By October of 1972, 3 ground test benches for Puma had been commissioned. In early 1973, T-6-1 received a new radar fairing with a blunted nose to improve millimeter wave performance. In March of that year, T-6-4, T-6-7, and T-6-9 tested an improved version of Puma, which sought to correct errors discovered when dropping bombs. From January to August of 1974, 661 flights were conducted across 15 aircraft. They launched a combined total of 15 Kh-28s, 50 Kh-23s, 12 R-55s, 4,000 unguided rockets of all types, 15,200 rounds from AO-19, and 10,000 rounds from SPPU-6. This resulted in the aircraft being recommended for adoption. On February 4, 1975, T-58M was officially accepted into service, under the designation Su-24, alongside Puma A, which received the designation PNS-24. With Su-24 in service, it was possible to focus on improving the capabilities of its computer. For this reason, aircraft from the 0304 series were equipped with Orbita 10-058M, which increased the system's memory from just 800 words to a long-term capacity of 24,576, with a short-term operational memory of 512. Like in MiG-27, Orbita performed dead reckoning of the aircraft's position, allowed for automatic flight along a predetermined route, calculated the coordinates of detected targets, alongside handling their automatic tracking, and computed gunnery, as well as bombing solutions. Shortly after the wide-scale adoption of Orbita 10, work shifted to the development of a successor that would make use of emerging solid-state technology, further miniaturized resistors and capacitors, as well as multi-layer PCBs. This would theoretically increase compute power to 200,000 operations per second, and reduce the number of microcircuits by a factor of 3. This would in turn increase reliability, reduce weight, and massively simplify production. Machines employing these principles came to be known as third-generation digital computers. E. Ignatyev at Elektro-Avtomatika worked to realize what would come to be known as Orbita 20, and determined methods for producing the multi-layer PCBs that would define the system. In 1971, a preliminary design was completed, just 1 year after it had begun development. Alongside Elektro-Avtomatika, the UFA instrument-making plant would begin work on software that would enter service with the computer. This would speed up its adoption by a considerable margin. This was made possible by the fact that Orbita 20 was the first of its type to allow complete software modularity without adjusting hardware. Only the memory devices would require replacement, after which 21 software modifications could be made. This would be further modernized with the introduction of erasable programmable read-only memory, in place of the read-only core rote memory. Once the software had been fully debugged, the reprogrammable ROM was replaced with a one-time programmable ROM, in which the data was permanently set by burning fusible links within the memory chip. This ensured more reliable long-term storage. Orbita 20 would make use of Tulip 3 integrated circuits, which were produced in Arsenyev and began development in 1968. The computer would go into production at the UFA instrument-making plant in 1974. Orbita 20 was employed in civil and military aviation alike. For this reason, nearly 15,000 were produced throughout its service life. The Orbita 20 family was made up of more than 10 unique modifications, which, like Orbita 10, were effectively identical, with the exception of memory capacity. The first aircraft within the VVS to make use of this new computer was MiG-27K. The variant designed for integration with the PRNK-23K navigation attack system was designated Orbita 20-23K. It is stated that the introduction of this computer provided a capability increase of 60% over the earlier 15-23 equipped airframes. One of the more significant advantages presented by 20-23K was the ability to run the entire navigation attack system through a battery of tests to determine if any errors were present, which made startup an exponentially easier process. However, the system was not without its shortcomings. Initially, 20-23K suffered from insufficient speed and failures to keep up with target displacement when the aircraft executed maneuvers. This led to additional automation being introduced, as the algorithms required to engage certain target modes were streamlined. This was achieved in an exceedingly short period of time, with considerable benefits. MiG-23BK, as it was known at the time, had never been more capable. After this revision, it was determined that a task requiring 7 MiG-27s could be accomplished by just 4, with an additional 45% increase in survivability against air defense weapons. At this time, Sukhoi was also working on the integration of the Kyra targeting system into what would become Su-24M, and faced similar difficulties, but the burden placed on Mikoyan was greater, as MiG-27 pilots did not have the benefit of a navigation and weapons specialist to correct any errors produced by the computer. It is for this reason that PNS-24M kept an Orbita 10 series computer, only improving its memory, likely for the sake of employing additional munitions. This variant would be known as 10-058K. Su-24MR, however, would retain the older Orbita 10-058M as part of the reduced NK-24MR navigation system, which was effectively PNS-24M with all of the ground attack functions removed. The first aircraft produced by Sukhoi to introduce Orbita 20 would be Su-17M4. Production capacity finally met demand, and it was possible to mandate the inclusion of a digital computer from the start of this variant's development, when it was originally believed that it would operate Orlan, a variant of Kyra. This, of course, did not materialize, and the aircraft ended up employing Klen 54, which was Klen PS with increased illumination range, which, alongside Orbita 20-22, made up the primary elements of the new PRNK-54 nav attack system. One of the limiting factors of the Su-17 series was the inability to employ multiple weapons in a single pass. On Su-17M3, this was technically possible, but had to be manually engaged by the pilot, which was difficult. Orbita 20-22 solved this problem, and for the first time allowed Su-17 to simultaneously employ two weapons. Orbita series computers would see use across a wide variety of aircraft not subordinate to the VBS, such as Tu-22M, Tu-144, Tu-95, Tu-142, Yak-42, and IL-86. However, information about the integration of Orbita series computers on these airframes is at best sparse and at worst dubious. The last aircraft that was planned to see Orbita 20 introduction outside of Su-25T was Su-27 KSH, a rather unique fighter-bomber proposal, featuring side-by-side seating and a targeting system akin to PNS-24M, using what was described as Kyra 12. This concept died along Project 1153. MiG-29 and Su-27 both employed variants of the C-100 computer, which was very similar to the Orbita series. C-100 began development at the Research Institute of Computer Engineering of the USSR, Ministry of Radio Engineering. Not much is known about the history of its creation, but 1982 is the recorded date of completion. In 1983, it entered serial production. In total, only 4,000 would be made. Technically speaking, specifications are very close to that of Orbita 20, with the most important integration being the revolutionary POISC architecture developed alongside it. Studies comparing Orbita series computers to C-100 determined that computers using POISC outperformed single-address machines by a factor of 2.5 in regards to productivity, and simplified software significantly. Initially, Sukhoi faced some challenges integrating the machine with the S-27U weapons control system. Without going into too much detail, in 1982 the program faced serious issues concerning radar development. In April of that year, an emergency committee of experts was formed within the Ministry of Radio Industry to review the situation and propose solutions. They concluded in May that it would be impossible to introduce Su-27 on schedule and meet the performance requirements with the current radar the team was working with. The committee drafted a myriad of proposals that were approved on June 7th, one of which called for a C-100 variant with increased memory capacity to be produced for the aircraft. In 1984, 846 flights took place. 40 of these tests involved T-10-10, T-10-18, and T-10-22, which were equipped with C-100 BZ-PP2, which introduced software that eliminated the need to manually input weapons carried by the aircraft before each flight. However, this early version did not support weapons yet to be tested on the airframe, only those that had been employed for the aforementioned avionics tests. And so BZ-PP3 began development in August to provide firing solutions for all of the munitions specified in the program requirements. In autumn of 1985, joint tests to determine the functionality of BZ-PP3 were completed following its integration with S-27 in August of that year, just 1 year after it had been proposed. In September of 1986, T-10-18, T-10-20, T-10-22, T-10-23, and carried out 127 flights, some involving the expenditure of R-27 and R-73. which resulted in BZPP3 being recommended for serial production. Between 1988 and 1989, a new variant, designated BZPP4, would be trialed and recommended for serial production, with the intention of increasing the efficacy of air-to-surface attacks conducted by the aircraft. BZPP3A, BZPP3D, and BZPP-SLI would be introduced, likely to expand munitions compatibility. Lastly, BZPP3-SLIFP would serve as an interim variant between 3 and 4. This concludes my relatively short video on the Orbita series and C-100. I hope that its length was not too upsetting. There is not a ton to say on the matter due to a limited number of sources discussing the development of these computers, and I wanted to focus on the history and impact of the Orbita series, rather than its technical specifications. Linked in the description will be a rather comprehensive look at how the 20 series computers functioned for any interested parties.